What if I told you the salt on your food, the minerals inside your bones, and even the batteries powering your devices all exist because atoms are willing to give away part of themselves? But why would an atom lose something as important as an electron? And why do some atoms steal electrons while others donate them? What makes two dangerous elements suddenly become stable together? For an answer of all these questions, today we're uncovering one of the most powerful relationships, ionic bonding, where chemistry gets dramatic. And by the end of this video, you'll understand why atoms form ions, how electron transfer works, why opposite charges attract, and how ionic compounds shape the world around us. So let's enter the invisible world of atoms, where losing an electron can actually make life more stable. In our last video, we explored why atoms bond, the drive for stability, the octet rule, and the race to fill that outer shell. Most atoms follow the octet rule. They want 8 electrons in their outermost shell. Like the noble gases and atoms have several kinds of bonding strategies to achieve stability, and ionic bonding is one of the most important of among all of them. Ionic compounds are commonly formed when metals react with nonmetals, when one atom has electrons to spare and another is desperate for more. On one side, you have atoms that want to get rid of electrons. These are typically metals, sitting on the left side of the periodic table. Sodium is a perfect example. It has 11 electrons total. 10 of them fill the first 2 shells completely. But the 11th? It's all alone on the outer shell. One lonely electron. And sodium desperately wants to lose it. Why? Because if it loses that one electron, its second shell, which is full, becomes the new outermost shell, instant stability. On the other side, chlorine. Chlorine has 17 electrons. Its outer shell has 7 electrons, one slot short of a full octet. It is desperately trying to gain one more electron. Sodium has an electron it doesn't want. Chlorine wants an electron it doesn't have. So sodium transfers that electron to chlorine. And the moment it does, something remarkable happens. Sodium, having lost one negative electron, now has more positive protons than negative electrons. It becomes a positively charged ion, called Na+. Chlorine, having gained one electron, now has more negative electrons than positive protons. It becomes a negatively charged ion, called Cl-. The positive sodium ion and negative chloride ion attract each other just like opposite poles of magnets attract. The powerful electrostatic attraction between these two oppositely charged ions is the ionic bond. Now you might wonder, ionic bonding isn't just about two atoms holding hands. In reality, billions of ions arrange themselves into giant repeating structures called crystal lattices. Every positive ion attracts surrounding negative ions, and every negative ion attracts surrounding positive ions. The result? A massive 3D structure locked together by strong electrostatic forces. That's why ionic compounds are usually hard, strong, and crystalline. Take common table salt, for example. Why is salt relatively hard and brittle? Because those ionic bonds in the lattice are extremely strong. It takes a lot of force to disrupt that perfectly balanced grid of charges. But when it does break, it shatters. Because when you shift the lattice, suddenly similar charges align next to each other. Positive next to positive, negative next to negative, and they repel violently, splitting the crystal clean apart. Sodium chloride is just one ionic compound, but there are thousands, and they share a remarkable set of properties because of how ionic bonds work. Now, let's discuss properties of ionic compounds. First of all, high melting and boiling points. Ionic compounds require huge amounts of energy to break apart. Why? Remember that lattice, that massive grid of tightly packed, strongly attracted ions? Breaking it down requires enormous amounts of energy. Table salt, for example, melts at over 800 degrees Celsius. That's why ionic compounds are solid at room temperature. Second property, electrical conductivity, but only under certain conditions. In solid form, ionic compounds do not conduct electricity. The ions are locked in the lattice. They can't move. Electricity needs moving charges to flow. But dissolve an ionic compound in water or melt it, and suddenly those ions are free. They can migrate through the liquid, carrying electrical charge. That's why salt water conducts electricity, but solid salt doesn't. Third property, brittle. Ionic compounds are strong, but also brittle. When pressure shifts the layers of ions, positive ions can suddenly line up next to other positive ions, and since like charges repel, the crystal breaks apart. Fourth, they tend to dissolve in polar solvents like water. Water's slight charge can pull ions away from the lattice. This is why so many ionic compounds readily dissolve, making them essential for biological and chemical reactions. So, where do we actually see ionic bonding in real life? You might think ionic bonding is just textbook chemistry, but it shapes almost every corner of your life. Ions are critical in your body. Your nerves use ions like sodium, potassium, calcium ions to send electrical signals through your body. Without ionic interactions, your muscles wouldn't move, your brain couldn't communicate, and your heart couldn't beat properly. When doctors give patients saline solution intravenously, they're delivering sodium and chloride ions directly into the bloodstream, using ionic compounds to restore the body's electrolyte balance. Coral reefs are built from calcium carbonate, an ionic compound. The ocean's chemistry, its pH, its ion concentrations, these determine whether coral can survive or bleach and die. Modern batteries, including the lithium-ion battery in your phone, work by moving ions between electrodes. Ionic movement is the power storage mechanism. When you take an antacid for heartburn, you're usually consuming magnesium hydroxide or calcium carbonate, ionic compounds that neutralize the excess acid in your stomach. The fertilizers that grow most of the world's food. Compounds like potassium nitrate and ammonium phosphate. Ionic compounds delivering essential ions to plant roots. From the food you eat, to the device you're watching this on, to the very electrical signals running through your nervous system right now. Ionic bonding is everywhere. Now, here's something every chemistry student loves. Ionic compounds have a simple and logical naming system. Let's briefly cover how ionic compounds are named, because the system is actually quite elegant. Rule 1. The metal, which is positive ion, comes first. Always. Rule 2. The nonmetal and negative ion comes second, and its ending changes to -ide. So, sodium plus chlorine is sodium chloride, magnesium, plus oxygen become magnesium, oxide, calcium, plus fluorine is calcium fluoride. When you see polyatomic ions, groups of atoms with a charge like sulfate or nitrate, their names stay the same. So, calcium plus sulfate become calcium sulfate. The naming system tells you exactly what elements are present and what charges they carry, a shorthand language that chemists use worldwide. So, let's come back to where we started. That grain of salt, the explosive metal, and the toxic gas. Now you know the full picture and saw exactly how that plays out in ionic bonding. Sodium transfers its lone outer electron to chlorine. Both atoms achieve the stability they were always reaching for. The dangerous substances don't disappear. They transform. Bonded ions behave entirely differently than free atoms. That's the power and the beauty of chemistry. Ionic bonding is the universe's way of turning dangerous, unstable things into something fundamental, stable, and life-sustaining. Salt, bones, nerve signals, battery power, ocean chemistry, all of it, built on the simple idea that opposite charges attract, and that atoms, like everything in nature, are always reaching for balance. Next up in this series, we're exploring covalent bonding. What happens when atoms share electrons instead of transferring them? It's a completely different strategy and it leads to some of the most complex molecules in existence. Link will be in the description the moment it's live. So if you enjoyed this journey into the atomic world, make sure to subscribe to Decoding Education and turn on notifications for the next episode. Because science isn't just formulas. It's the story of how the universe holds itself together. See you in the next video.